This part of the module is about generalizing what we learned about matrices and vectors in the previous part. But before we get to that, we need to think carefully about the actual entries of those matrices and vectors. So when we talk about vectors, matrices, or scalar multiplication, we have to decide what those entries are and which scalars we're allowed to multiply by. All the examples we did were of matrices and vectors where the entries were real numbers, in fact even rational numbers most of the time, but it wouldn't have made any difference to the things that we proved if they were complex numbers instead. But on the other hand, suppose that we insisted on working only with matrices and vectors whose entries were integers. Now in that case, a lot of the results that we proved in the previous part of the course would not be true. For example, we know that every matrix can be put into row-reduced echelon form by doing a sequence of row operations. But if you start with the 1 by 2 matrix 2, 1, like this, then you can't do row operations to this and end up with a row-reduced echelon form matrix whose entries are integers, because you know that when you do row operations to this to get into row-reduced echelon form, what you would end up with would be 1, 1/2, and of course the entries here aren't integers anymore. So that suggests that some of the things that we proved in the previous part of the course wouldn't be true if we only allowed the entries of our matrices and vectors to be integers. So it's natural to ask what kind of numbers you can use as your entries in your vectors and matrices, and what kind of numbers you can use for scalar multiplication if you still want to be able to prove all the results we proved in the first part of the module. And the answer to that is the entries must come from what is called a field. Now informally, a field is a set which has an addition and a multiplication defined on it, in which all of the usual rules of algebra apply, and in which you can divide by any non-zero element. Examples would be the real numbers, or the rational numbers, or the complex numbers, and examples of things which are not fields would be things like the integers. And the reason for that is that you can't divide an integer by a non-zero integer and expect in general to get another integer. If you divide 1 by 2 or 2 by 3, the answer is not an integer again. That definition of a field was a little bit vague, so on the next slide we're going to look at a formal definition of a field. It's not going to be something which is especially important to us or which we're going to return to very often, but I'm going to write it down here, and I have written it down here, so that we can see the precise definition. So here it is. A field is a set F containing special elements 0 and 1, and equipped with addition and multiplication, such that for any three elements A, B and C in F, the following rules hold. First of all, we have a commutativity property. A plus B must always be equal to B plus A, and A times B, which we would write just by putting A and B side by side, must always be equal to B times A. Next, A plus 0 should be equal to A for any A, and A times 1 should be equal to A. Next, both operations should be associative. A plus, in brackets, B plus C should be equal to brackets A plus B plus C, and A times B times C should be equal to A times B times C. Those are called the associativity laws. We should also have distributivity laws, which say that A plus B times C should be equal to A plus B plus A times B plus A times C, and A times B plus C should be equal to A times B plus A times C. And finally, there should be two rules about additive and multiplicative inverses. First of all, for each element A in F, there should exist another element called minus A in F, with the property that A plus minus A is equal to 0. And next, for each non-zero A in F, there should exist an element written A to the power minus 1 in F, which has the defining property that when you multiply A and A to the minus 1, you get 1. So these are what I mean when I refer to the usual laws of algebra holding in any field. Furthermore, you can see that we already know lots of examples of fields. You could take the real numbers R. This obeys all of the rules on this page. You could take the rational numbers Q. That means all of the fractions where the numerator and denominator are integers. So A over B, where A and B are integers and B is not 0. Or the complex numbers. Those would all be examples of fields. But we have some examples of things which are not fields. The integers, for example, are not a field because they don't obey the very last rule here about multiplicative inverses. There is no integer which when you multiply it by 2 gives the answer 1. And there's no integer which when you multiply it by 57 gives the answer 1. So it doesn't obey this last condition. It's not a field. Equally, if we talk about the set of all 2 by 2 matrices with real number entries, this isn't a field either. Pause the video now. Think about which of these rules is not obeyed by the 2 by 2 matrices with real entries. And there might be more than one. Okay, I hope you did that. If you did, well then you'd notice that, of course, this rule is not true anymore. Not every non-zero matrix is invertible. And equally, there are other rules which aren't true as well. So, for example, matrix multiplication is not commutative. So this rule doesn't apply either. Okay, we've seen some examples of fields. We've seen some examples of things which are not fields. We're now going to move on to a family of examples called the finite fields of order P, which are much more which are new to us, which are very interesting, and which are quite different to the fields that we've seen so far. So for each prime number P, so this P here must be prime. For each prime number P, there is a field written as a bold F with a subscript P, called the finite field of order P, whose elements are ordinary integers but in which we regard two integers to be equal if and only if they differ by a multiple of P. Another way to put this would be to say that two integers are regarded as equal in the finite field Fp, if and only if they're congruent modulo P. We met the congruence relation, congruence modulo P relation during the first part of Math 5. So in particular, in Fp, all multiples of P will be equal to 0. And the reason this is called the finite field of order P, so order usually means size, is that in Fp, every element is equal to one and only one of the numbers 0, 1, 2, up to P minus 1. Let's see some examples, or let's work with some examples. So let's take F5 to begin with. That's the field of order 5. And in F5, the elements are written as ordinary integers, but we regard two integers as being equal when they differ by a multiple of 5. So that, for example, minus 3 would be equal to 2, as minus 3 and 2 differ by a multiple of 5. And that would also be equal to 12, and that would also be equal to 7. And if we now take a slightly different example, let's look in F3. So in the finite field F3 of order 3, minus 2 will be equal to 1, and that would also be equal to 4 and 7, and minus 1 will be equal to 2 and 5 and 8, and minus 3, and any multiple of 3 will be equal to 0. So 66, for example, will be equal to 0. Now, of course, fields aren't just sets, they have addition and multiplication. So for practice, let's do a little bit of arithmetic in these finite fields. So in F5, we're going to do some sums. 3 plus 4, well, that's equal to 7, of course, because the addition in F5 is the same as the ordinary addition, except that the elements are elements of F5. So 7 would also be equal to 2. And if we do some subtraction, 3 plus minus 4, 3 minus 4 is equal to minus 1, and that's equal to 4. Let's now do some multiplication. So 4 times minus 3 will be equal to minus 12, and minus 12 is equal to 3, and 2 times 4, that's equal to 8, and 8 is equal to 3 in F5. So going back into F3, again, let's do a little bit of arithmetic. 2 times 2 will be equal to 4, and of course that's equal to 1 in F3, because 4 and 1 differ by a multiple of 3. 2 times minus 3 will be equal to 0, because 2 times minus 3 is minus 6, and every multiple of 3 is equal to 0 in F3. If we do minus 1 times 2, that will be equal to minus 2, and minus 2 is equal to 1. And of course, 2 is equal to minus 1 in F3. Now there's an easy way for us to summarize all of the possible additions and multiplications in a finite field of order p, which is by drawing up a table where the rows and columns are the numbers 0, 1, 2 up to p minus 1, and in row I and column j we put the result of I plus j, or I times j, in that finite field. So here are addition and multiplication tables for, first of all, F3. So in this entry, for example, what we're saying is that 1 times 2 is equal to 2 in F3. Well, no surprise there, but let's look at a more interesting example. So this box here is the multiplication of 2 times 2, and we know that here 2 times 2 in F3, well, it's equal to 4, and that's fine, but in the entries of these tables I've tried to use only the numbers 0, 1 and 2. So 2 times 2 is equal to 4, and in the finite field F3 that's equal to 1, because 4 and 1 differ by a multiple of 3. So next let's look at the finite field F5. So this time I've missed out some entries in my addition and multiplication tables. A good thing for you to do right now will be to pause the video and fill out the empty squares in these addition and multiplication tables. I'd like the numbers which go in there to be numbers between 0 and 4. Okay, I hope you did that. Let's work out some of them. I'll show you the full answer on the next page for the multiplication table at least, but let's work some of them out. So in here, the square I've just indicated, this should be 3 times 4 in F5, and 3 times 4 is 12, which in F5 is equal to 2, so that should be a 2. And of course 3 times 4 and 4 times 3 are the same, so I can copy that number here. And if we want this box, that should be the result of 4 times 4 in F5. 4 times 4 is 16, which is 1 in F5. 3 times 3 is 9, that's equal to 4 in F5. And similarly, let's do the addition. 3 plus 3 is 6, which is 1. 3 plus 4 is 7, which is 2. 4 plus 3 is 2 again. And 4 plus 4 is 8, which is 3. So in a field, we're supposed to be able to do addition and multiplication in such a way that the normal rules apply. And we're also supposed to be able to divide by non-zero elements. So in F5, for example, I should be able to divide by every non-zero element. For example, I ought to be able to do 3 divided by 2. So what is 3 divided by 2 in F5? We're going to think about the answer to this. One way to do that is to say, well, if x is 3 over 2, then 2 times x equals 3. So what we can do in order to find what this number 3 over 2 should be in F5 is to look at the multiplication by 2 row of our multiplication table, which I've copied down here. There's the row or the column for multiplication by 2. So we want to multiply some number by 2 and get 3. And you can see, looking at this table, that the number which you multiply by 2 to get 3 is 4. Right, there we go. 2 times 4 is equal to 3. So from the table, x is equal to 4. Okay, so in F5, 3 divided by 2 is equal to 4. Let's try another piece of arithmetic in F5. So what is 1 divided by 3 in F5? It ought to be equal to one of the numbers 0, 1, 2, 3, but which one? Well, again, we can work this out simply by looking at the multiplication by 3 row in our multiplication table, because 1 over 3 must be a number which, when you multiply it by 3, you get 1 again. So here is the row for multiplying by 3, and you can see that the number which you have to multiply by 3 to get 1 is 2. That's according to this entry here in the table. So 2 times 3 is equal to 1 in F5, so 1 divided by 3 is equal to 2. Let's do some more. So a slightly more complicated piece of arithmetic. Can we solve a linear equation 3x plus 3 is equal to 2? So this will be a pretty typical piece of homework for somebody who's just learning how to do algebra with the real numbers. We're now going to do that same piece of homework in the field F5. And we're going to solve it exactly the same way you would solve this if it were an ordinary equation in real numbers. We'll move the 3 over to the other side. So we get 3x is equal to minus 1, which, if you like, is equal to 4. And then we would have x is equal to 4 divided by 3. So that's 4 times 1/3. We know that 1/3 is 2 in F5, so that's 4 times 2, which is 8. And 8 is equal to 3 in F5. Okay, so I think the solution to this linear equation is that x must be equal to 3. Let's try and check whether we got this correct. It's always good to check your answer. So check by substituting back into the original equation. What happens? 3 times 3 plus 3 is equal to 9 plus 3, which is equal to 12. And that really is equal to 2. So that was what we were supposed to get. We have the correct answer. And we've done. We solved our linear equation. Okay, so we can do all kinds of ordinary algebra in our finite fields. One of the tricky problems here was that when we wanted to do a division in our finite field F5, we basically had to do this just by writing out the whole multiplication table and searching that table to find what number, when you multiplied it by 3, gave you the answer 1, or what number, when you multiplied it by 2, gave you the answer 3. And that's fine for small finite fields like F5 or F3, but what if you wanted to work in some larger finite field like F101 or F65537, right? If you wanted to know the answer to 1 over 13 in the finite field F101, you don't really want to have to be working out all of the multiplication by 13 row of that table, or even worse, if you wanted to know 1 divided by 13 in F65537, you absolutely don't want to be working out the whole row of the multiplication table. So it would be much better if there were a more systematic way to do division in these finite fields of order p. And that's what we're going to look at in our next video.